All right, so we're going to look at reaction mechanism. Reaction mechanism is what is occurring on a molecular level. So when we say, for example, that um, carbon monoxide is reacting with oxygen, we really do mean one carbon monoxide molecule is going to react with one oxygen molecule, and we're going to make some products. And these two have to come together on a molecular level, one to one. So DN reaction mechanism is we're looking at it on a molecular level. So first of all, you're going to be given a series of elementary steps or elementary reactions. Now, the elementary steps are going to lead to the product. And these elementary steps, as we have all of them in here, we're going to call this set of elementary steps the reaction mechanism. Now, frequently in these elementary steps, we're going to make something and then we are going to use it up, something that might be in a transition state. So if we have, in this case, two NOs go into N2O2, in the middle here, we're saying that we are making some N2O2. It's not in the final reaction. And if it's produced and used up, it is going to be an intermediate in this reaction mechanism. Note, these are always going to be given to you when we're looking at our mechanisms. So we need some rules. So when we have our elementary steps, if we have one reactant going into products, one of the rules is that the rate, so here, our rate, for our elementary step has to be written directly from the reaction, which in this case says A goes into products. So our rate says that our rate depends on how much A we have. There's nothing else in here, therefore there's nothing else in our rate. Because this is one molecule, we say this is unimolecular. For the next one, we have an A plus a B, meaning that these two have to come together and collide to make products. So our rate is going to be how fast A can find itself some B. This is going to be two reactant molecules involved, and we say this is bimolecular. We could even have two A's going together to make products. Our rate is now going to be how fast each of these A's come together, hence A squared. Because this is still two reactant molecules, this is also bimolecular. If we had three going together, if we had an A plus a B plus a C, we would have three different things, and our reaction rate or our step would be termolecular, three things coming together. The elementary steps have to add up to give us the overall balanced equation. And again, these are always going to be given to you. Someone's going to give you the elementary steps. Intermediates, again, are produced in an elementary step, then immediately used up or consumed. Now, in a lot of reactions, we're going to have a slow step. We call this a bottleneck or a rate determining step. This would be like being stuck on a freeway. So if you're on the freeway and you're driving along, and then suddenly you're finding that you've got a bunch of lanes that are closed, and you have everybody in these three lanes merging down into one lane. And this is going to be the slow point. And this would be like if you had a bottle. I know I can't draw here. Getting everything out of this bottle depends on how fast you can get through that small part. That's called a bottleneck or the rate determining step. The rate determining step is the slowest step in the sequence, and the slowest step or the rate determining step should predict the same rate law that is determined or observed experimentally. With a note, we can't have intermediates in our final rate law. So, we've got some rules. So let's look at this one. If we're looking at the reaction between N2 and CO to make NO plus CO2, and we are given that the experimental rate is K times NO2, the quantity squared. And we are proposing, and these are always proposed unless you go to lab and prove them, which is pretty darn tough. We have to take and do this using two steps. So first of all, what's the equation for the overall reaction? The overall reaction we add, and we take a look. Please notice that NO3 is produced and used up. Therefore, NO3 is an intermediate. We're going to cross it off. And our net reaction is NO2 plus NO2. And then we go, whoops, and NO2 comes in and comes right back out again. So that's not the case either. So we're going to take an NO2 out of here. And we're going to say that NO2 reacts with CO to make NO plus CO2. If a reaction is used and then reproduced, in fact, is going to be a catalyst. So our intermediate is NO3. What can we say about the relative steps? Well, please note our rate is equal to K times NO2 squared, which tells us that our rate has to depend on how fast these two get together, meaning that this has to be our slow step. After we make our nice NO3, it's going to react very quickly with the NO to produce products. So what do we say about the relative rates? One is slow, and from what we can tell, two is going to be fast. Now, something that is very common in these is a fast initial step that ends up being at equilibrium. So we need to be very careful to define equilibrium. Equilibrium, by definition, is when the rate of the forward reaction is equal to the rate of reverse reaction. So if we have, for example, A squared is going to go into equilibrium, and equilibrium, we are consistently going to use two arrows, just like this, to describe equilibrium. So let's say that A squared goes into 2A. Because we have two steps here, we're going to put two rate constants, and we're going to call it K1 and K minus 1, where minus 1 would be the reverse. The rate forward is going to equal K1, the rate constant by which A squared goes into A2, multiplied by what we see in that reaction, which is A squared. It is going to equal rate reverse. Well, rate reverse is this K minus 1, multiplied by the A's going back. Now 2A, by the way, is A plus A, which is going to be the same as A squared. That is going to be equilibrium, and that's going to be rate forward is equal to rate reverse. Now we're going to find this is very handy because we frequently have fast steps that contain intermediates, and we're going to have to be able to express the intermediates in terms of reactants because intermediates cannot be in the final rate law. So the only way to do this is to simply do this. So let's take a look at this one. So first of all, we can always take our reaction and we can write our overall reaction for this. So first of all, this is fast in equilibrium. This is slow, meaning this is our rate determining step, and we always write our rate law from the slow step. So we're going to say that rate is equal to K2 multiplied by hydrogen multiplied by N2O2. We're just going to take our rate constant. In this case, we're going to go K2. Why? Because it's step 2 multiplied by the concentration of the reactants. The last step we're going to say is fast. So our first step here is at equilibrium, but we've got some problems here. And one of our problems is that we have two intermediates in this reaction. One intermediate is N2O2, and the second intermediate is N2O. How do we know? We know the intermediates because they are produced and immediately used up. So we have intermediates. And we have a rate law from our rate determining step. And we're saying that, hey, if we go to the lab, we should find that the rate is going to equal K2, how fast that particular rate is, multiplied by how much hydrogen we have, multiplied by N2O2. But there's a problem. N2O2 is an intermediate, and we can't have intermediates in our rate law, mostly because we can't find them. It's too hard to do experimentally. So what do? Go to the equilibrium step, and we solve for N2O2. So 1, we're going to write the rate law from the slow step. Second, we're going to write the rate law from the equilibrium. And solve for an intermediate. So almost always we're going to get an intermediate in this mess, so we're going to solve for an intermediate. All right, so that's going to be our process. All right, so let's continue with this. We know that our rate is going to equal, remember we called this K2, K2 multiplied by hydrogen times N2O2. Now we need to go to our equilibrium step and remember what this means. We know at equilibrium, our rate forward is equal to our rate reverse. And when we do this, we're simply going to find the Ks. So the rate forward is this one going in this direction, and that's simply going to be K1, that's the forward K, multiplied by our concentrations, which is NO squared. There's two NOs, so we got to square that, is equal to rate reverse, which is K minus 1 multiplied by N2O2. So we have nice equal sign, which means we can solve something. We're going to solve for the concentration of N2O2. Why? Because it's in our rate law that we have from our rate determining step. So let's solve for N2O2. When we do this, we're going to get N2O2 is equal to K1 over K minus 1 multiplied by NO squared. And we're going to plug this in for that. When we plug that in, we're going to get rate is equal to K2 times K1 over K minus 1 multiplied by hydrogen times NO quantity squared. At the end, we realize that all of our Ks are just a number, and we stop separating them, and we're just going to call it K. So our final rate law is rate is equal to K times hydrogen times NO, the quantity, squared, from our given mechanism. All right, let's do another one. We have a fast step that is at equilibrium, and we have a slow step. So we've been asked a few things. One, what is our overall reaction? Well, our overall reaction is we're going to add them up. We're going to realize that NOBr2 is an intermediate, and our overall reaction is going to be 2 NOs plus a Br2, just adding this up, goes into 2 NOBr. So overall reaction. From our slow step, we say that our rate is equal to, and we have to put K's on this, so we're going to call this K2, again, only because it's step 2, multiplied by NOBr2 times NO. So NOBr2 is an intermediate, so we have to go to step 1 and solve for it. So solving for it using the equilibrium step, we have rate forward is equal to rate reverse. Just shorthanding this, and we're going to have K1 multiplied by NO times Br2 is equal to K minus 1 times NOBr2. If we solve for NOBr2, our intermediate cannot appear in our final rate law. That's going to equal K1 over K minus 1 times NO times Br2. And we're simply going to plug that in up here. And when we do this, we're going to get rate, combining all of the K's to just call it K, multiplied by NO, and there's two of them, one here and one here, so we're going to square it, times Br2. At that point, we can answer the final question. Is this mechanism consistent or valid? Do we know it's true? No. To know if it's true, we have to go to the lab. But is it valid? Yes. It is the same form as what is observed from the experimental data. All right, quick jaunt into catalysts. Catalyst alters the rate of a reaction by frequently lowering the activation energy. It does it by either increasing the number of effective collisions, thus making our A factor bigger, and it frequently provides an alternate pathway, and this alternate pathway has a lower activation energy. And because it has a lower activation energy, it is going to speed up the reaction. So catalysts speed up reactions by providing in general a lower activation energy. We have two kinds, homogeneous and heterogeneous. Homogeneous means same phase as the reactant. Heterogeneous is going to be in different phases. Let's look at some examples. All right, so if we're looking at the destruction of ozone, chlorine and the destruction of ozone is in the same phase. They're all gases. On the other hand, a catalytic converter in your car is going to be solid metal pieces, sort of in a powder that the products out of your combustion can react with to make it into stuff that's nice and clean, or cleaner at least. So if we put a catalyst into a reaction, it is going to provide a lower activation energy of the catalyzed, meaning that you don't have to get as hot for the reaction to occur. The catalyzed pathway can frequently have more than one step, so it can totally change the actual mechanism of the reaction when you put one in. How does it change it? You have to go to the lab and figure it out. Please go onto the internet and look at the ozone hole. We need to look at the destruction of ozone. And if you take a look at that, and by the way, that's going to be on your study guide, you're going to realize that chlorine that we produce or produce because we use chlorofluorocarbons has gone up into the ozone layer. And we're looking at here the ozone layer, particularly at the poles, both the North and the South Pole, and the chlorine actually is a catalyst for the destruction of the ozone layer. It goes in, reacts with ozone, and it comes straight back out again unused. Makes it very dangerous, lowers the activation energy, and it comes right back out again to destroy more ozone. Why do you care? Ozone absorbs ultraviolet, and ultraviolet is what keeps us from getting sunburned and all sorts of other things.